Good afternoon, everyone. Thank you for coming. We have great guest today. We have Angus Gentle from UTS. A lot of you know him. It seems like we visit his lab more than we visit our lab.
Yeah.
Well, at least some of us. So Angus did his undergrad in UTS and then completed his PhD, I think 2008, something like that. And then he came here for 1 year postdoc with Gavin on quantum dots. And after 1 year back to UTS as a research fellow. He has great experience in every optical measurement and has a lot of experience not only for solar cells, but a lot of, I assume most of collaboration with us is optics for solar cells. Every time that I meet Angus, I learned a lot, not only how to drink beers, but also a lot of optics. But I think the first time that I'm going to hear Angus as a speaker, so it's quite exciting to hear what he wants to tell us about optical properties of material. So, Angus, the stage is yours.
Thanks, Steve. Yeah, so as it says up there, we're now at the School of Mathematical and Physical Sciences as part of Faculty of Science. We used to be the Department of Applied Physics, and they sort of joined physics, chemistry, and maths together a few years ago when we moved into our new building. So we're the kind of wobbly-shaped building behind the tower, where we are. So a quick overview of the talk. I'll give you a bit more background about what sorts of things I've done, different research we do at UTS, and then the different optical characterization techniques that we do at UTS that you might find interesting that you can do some more collaborations on. Because every now and again we have someone come along saying, oh, we'd like to do this, and we say, yeah, talk to Ziv and Matthias, they know exactly what measurements we can do, so thought we'd give you an update on what we can actually do. So most of the research I'll be talking about is stuff that we've done with Jeff Smith, Matt Arnold and Mike Cordy and our various students over the years. So basically I did applied physics and electrical engineering undergraduate, and during my undergraduate we did an internship project where I started working there in 2000 and then continued on ever since, working in the lab part-time while I was doing the degree, which is a great way to learn hands-on skills while you're learning all the theory. Then went on to do honours and postdoc. So the PhD I did on nanostructured materials and looking at the optical properties of them. And as was said before, I worked out here for a year with Gavin 10 years ago now. So then went on to do radiative cooling. So we sort of started doing radiative cooling before radiative cooling was cool. When we first published the stuff on radiative cooling in nanoletters, there was hardly any citations at all for quite a long time because no one really knew what we were talking about. And then eventually the guys at Stanford picked it up and went, oh, that's really cool. And then everyone went, and it took off, is basically what happened with there. After that project, moved on to doing a transparent electrodes project. It was one of the CSIRO cluster projects. So that was with UQ, UTS and Flinders. So basically we were looking at alternatives to ITO, and so looking at for OPV and OLEDs, but it applies to lots of other sorts of ones as well. Since then moved on to another DP doing the short title of it's basically angular and spectral control. So rather than just looking at the spectral selectivity, looking at varying the angular and spectral selectivity for particular things. And then 2016 I got a permanent position, so that was good. So ended up as a lecturer there at the moment. So I pretty much teach second year and third year subjects on applied electronics, computational physics and measurement analysis, which is basically like a project subject where they learn data analysis and then build lots of projects. So it's sort of like the one that Ivan and that do for their undergraduate, what's it called, something like that? Yeah. What's your subject called? No, the research, undergraduate research project, the end one, where you do the two big groups and you split it in half. Advanced characterization, yep. You put advanced in it because it makes it sound cool. Yeah, so that's basically it. So most of our research is optical properties of materials, whether we're characterizing someone else's material, making your own material from scratch, or getting a material that people haven't actually looked at much before. So that pretty picture at the top is actually a slide that we made. So it's made up of 5 layers of silver, alumina and silver, and it's tapered thickness of the alumina. So it ends up being a resonant cavity between it, so you can transmit, so it's put on a scanner and that's the transmission going through at different ends. So if you put that in front of a camera and slide it across, you can do hyperspectral imaging as you go through. So that was quite a nice one. I like to include it in because it looks pretty. So basically we look at lots of different nanostructured films, whether it's different random structures or multi-layers, a lot of spectrally selective coatings for lots of different applications. Radiative cooling, we do a lot of things on. We work on paints, so it's not just thin films. We do a lot of sputtering sorts of things, but paints, Then going up to what happens when you put the paints or windows on a building, doing the full-scale thermal modelling of buildings and measuring buildings as well. So working with other companies on measuring it, see how much energy gets saved, so does the model actually work. We had one project with CSIRO looking at their Nathers engine, which is basically the building rating model. And so we're looking at how well does it model the roof. So we've got some cubbies that we built on the top of the UTS building, and we can change the roofs and the insulation and those sorts of things up there. Transparent electrodes and optical characterisation. So that's the main sorts of areas we work on. So, optical properties, what we're interested in is, does it absorb, transmit or reflect? And if it does absorb, where does it absorb? So if it's in a device, does it absorb in the right spot, give you carriers that aren't recombining at the contacts, those sorts of things. Characterising that, analysing it, fabricating different structures and looking at what you can use them for. So unlike you guys who go, I'm working in solar and I'm working on this particular type of cell, we work on absolutely anything. If something sounds interesting, we'll go and do it. So that's why it works quite well for collaborating with different people, because if something goes, yeah, that sounds good, it fits in with what we're doing, we'll jump on it. So here's some little pictures we have from different ones. So this one here was from a paper where we were de-alloying. So we do some gold sponges. So you start with a gold aluminium sponge, alloy, so AuAl2, it's purple gold. You put it in sodium hydroxide and it de-alloys into a really porous, nanoporous sponge. And so people had always wondered, how fast does it actually etch? So some groups had done it and you etch it for a little bit, take it out, do TEM and go through. We put it in a little cuvette with a spectrometer on it and then measured it, the spectrum every second as it etches it out over however long, and then did the optical fitting of it so you could actually work out the etch rates. So it's a way of doing in situ analysis of a material. And so since then we've also then gone, you can also look at how far through you are and what the process is going on by just measuring the current that forms from the aluminium coming out. So that's another one we've been doing with that since. This is a pretty picture from a paper we put out earlier this year on some self-assembled nanofins. So on the figure A there, that bar is 500 nanometers long. So you've got micron long fins which stick up about 200 nanometers across and 50 nanometers or less the other direction, made out of molybdenum, those ones were. So they're refractory, so you can heat them right up, very stable. They're also polarizing. So to start with, they've got a continuous metal film underneath, so you can do it as a self-assembled polarizer that reflects. We can de-alloy the aluminium out of it. So it's a combination of molybdenum and aluminium. De-alloy the aluminium out, and on that picture there, that's an SEM of the de-alloyed one. So it actually goes and aligns really, really well, self-assembled as a polarizer. And so above there, that's an image through these glasses. We bought a pair of glasses from the cheap shop across the road, put the glasses in the chamber, deposited it, tested it out, went outside, took some photos of the sky, and you can see it actually was polarizing. And down the bottom, it's showing your extinction coefficient. So basically, it's the extinction ratio between the two different polarizations in there was about 100 for something that you basically start off with two things that are deposited sputtering, and they interact, so it self-shadows, grows this really nice tall fins, then we etch it out. So it's quite a simple process to make it instead of these different techniques that other people have done for it. And so we'll be looking at, modelling, deposition and characterisation at all different scales. So whether it's materials-based, nanoscale things, microstructure, or going up to what happens when you put it onto buildings. So we'll look at surface effects of, one of the things that I know people here look interested in as well is when you have a surface, if you roughen it up, what happens to the emittance or the reflectance? How much does it change? So we sort of work across all those different scales and lots of different wavelengths as well. So I gave a similar talk this recently for some communication students, and on that one I had to talk about how much sun you get. Here I'm not going to worry about that part because hopefully you know. So basically you've got the sunlight. Most of the cells you look at are 1 micron down. And so if you look at how many watts you've got of incoming solar, about 1,000 watts per square metre coming in. And then if you look at the far infrared, you can look at how much heat is coming down from the atmosphere and how much infrared is being radiated from the actual surface as well. And so you'll see here that even though this is quite a small intensity compared with that one, when you sum it up, it's quite large because it's over a lot of different wavelengths. And so that's the thermal image of UTS. This was a few years ago when we got a thermal camera on the roof and went, oh, that looks quite nice. So you can see how incredibly thermal efficient the big brown tower is at UTS. So if you split it up into the different components, how much sun you're getting at different times of the day, and then go, what's the 24-hour average, you end up with about 240 watts, 24-hour global average for sunlight. If you then look at how much is coming in from the atmosphere and how much is going out from surfaces, you'll see that the amount of heat coming in from the atmosphere is actually larger than the amount that's coming in from the sun. It's just that the most surfaces you have at the same time are also radiating, but if you design a surface which radiates at particular wavelengths, you can then start to exploit this imbalance between these two here and get a continuous amount of power. So the reason this works is because of water vapor transmits really, really well in a particular wavelength range. And so people talk about sky window or sky window selective absorbers. They're things that absorb very strongly in the area where the atmosphere is perfectly transparent or close to transparent. And so when we're looking at CO2 and people are talking about very small percentage of CO2 changing how much heat gets radiated out at night so it gives you global warming, it's actually this very, very small amount down here that's causing, it just happens to line up perfectly with where the water vapor doesn't absorb. And so that's why if you've got a cloudy night or it's very humid, it doesn't get as cold at night. And so if you're in a desert and it's very dry, it gets very, very cold at night because you're radiating out a lot more. So basically the amount of heat that comes in depends on what the atmospheric conditions are in your place and at that time. And so you can see here the different scales for, so in irradiance, how many watts per square metre per micron for solar. It's a lot higher, but there's a lot more wavelengths you're summing up over to do it there. So spectrally selective absorbers, different coatings, if you're doing broad ones as opposed to, sometimes you might do an emitter where it's for, say, a TPV sort of thing where you want a very narrow emitter just above a bandgap. If you're looking at just solar thermal absorber, you want it black in the solar range so it absorbs strongly, very white in the infrared. Cool paints, you want the exact opposite. And so that's why you end up doing these same techniques across lots of different fields because it's really the same thing, it's just optics. And then you can also start looking at cool coloured paints. So years ago we put out one of the first papers on how you could make cool coloured paints in 2003, where basically you could put a coating on that's absorbing strongly in the visible, but it's reflecting strongly in the near infrared, so then you can start to get a cool paint. So it absorbs in the visible in some wavelengths, reflects the near infrared, but then absorbs strongly again in the far infrared, so thermally the emittance is still high. And so one of the reasons why you can get that relatively easily is that the polymers absorb strongly in the infrared, so the binder itself does the last part for you, then it's just tricks in the visible solar range to actually get it to work properly. And then a slightly more selective one is if you've got a sky window selective emitter, is if it's sort of black between 7 and 13 micron. There's been lots of papers by people saying, oh, how great it is and this is where you want to be working. It's true in some cases depending on what temperatures you're operating at. Because if you limit the spectral emission, you limit how much power you can put out. So I'll sort of go into that. I've thrown a bunch of different papers at the bottom, so different slides, so if people want to look up different ones. So if you want to look at the lumped cooling, for some reason this is a little like that, so I'll go there. So basically, you can look at it spectrally and then build up each wavelength at a time, or you can just look at the lumped terms. So the amount of thermal cooling you get is basically based on how much sunlight gets absorbed. So at night time you get 0, daytime might get up to 1,000 if you've got something absorbed strongly. How much parasitic conduction you're getting to your roof or to whatever else you're attached to. So if you're trying to make something that gets very, very cold, you insulate it very well and try and get the parasitic cooling or heating minimized as much as possible. Convection across the top surface. So if you've got air blowing past, if it's something that's hot, convection cools it. If it's colder than ambient, the convection warms it back up. So sometimes you might do things where you put a convection suppressant. The most common one people do for things where you need a radiator is you do a piece of glad wrap. So 10 micron thing. Often people will say high density polyethylene 10 micron, it's glad wrap. And so one of the problems with that is you get rain forming on it and then the water blocks the emission. So one of the tricks we did for that was you put a mesh instead. So you can buy lots of mesh for putting over crops, which are supposed to be sold so that they stop frost and keep animals off. So we bought one that was actually said stopping frost, but they said stop frost and made from high density polyethylene. So high density polyethylene is transparent in the infrared, so it actually encouraged frost. It was really quite a good product if you wanted to destroy your crop. So if you're ever trying to protect a crop, don't buy a high density polyethylene one, get a polyester one instead, or a PET sort of mesh. And so that way you could have it so it would still radiate out through the mesh, but it wouldn't work quite as well, but you didn't have any problems with heat being trapped in the daytime. So if your sample got hotter than ambient during the day, if you've got a cover over it that doesn't let air through, builds up heat and it causes a problem. If you've got an open mesh, the convection, because it's hot, comes up, goes through, but at night time it can still get cold. So first of all, we sort of started off doing all these tricks at night time, then sort of moved on to daytime things later on. And so how much radiation comes out from a surface, you take the hemispherical emittance, and then you've got a really standard equation that hopefully all of you know and recognize. And how much radiation comes in from the sky. Basically, you've got radiation that comes in from up above and all different angles. You get different amounts from different angles because of the transparency of how much distance you're traveling through. And so you can measure it with a single instrument, or you can look at it spectrally, as with most of these things. So downwelling infrared from the sky, you've got your pyrogeometer. So they're measuring basically 4 to 50 microns. You can look at how much is coming down over the day. Usually you get between about 240 to 400 watts per square metre in Sydney. Some places will get higher or lower depending on how humid or how hot they are, because it's all related to a T to the 4 equation. And so that's happening all the time, coming down. At the same time, you've got a distribution of temperatures. So if you get a cheap infrared camera, you can look up and see the effective sky temperature using one of those. So it's a really quick way to measure how much is coming in. So if you point it directly up, you'll see it's quite transparent, so it's cold because you don't get much heat coming in. If you go down to a little bit of an angle, you'll see, it's getting warmer. Just above the horizon, you're seeing an effective sky temperature of about 0 degree. And then as you go down to the ambient temperature, it goes up to, in this case it was about 24 degrees, and it was minus 20 straight above as the effective sky temperature. And so that's basically because straight up, it's relatively transparent. You don't get much radiation coming in. That bumps your CO2 bump. As you go up to higher angles, you're getting more and more radiation coming in because it's less transparent. You also get this other thing that when you start off at ground level, the air temperature drops off at a lapse rate of 7 degrees per kilometre as you go up. So you've really got to, if you want to try and look at it spectrally, you've got to sum it up over the distance as well as, you can't just go, it's that way and it's this temperature, which is what some people do. So if you have the transmission spectra of how much goes through at different angles, you can get the transmission at the zenith, and then simple equation to work it out for how much. Then you can look at how much is being absorbed by your sample at each of these different angles, because you can measure your reflectance of whatever surface you have. So if you don't want to do the lumped hemispherical emittance, you can calculate at each angle and sum it all up. So because you've got this pattern, which is you want to emit more straight up and emit less further out over certain wavelengths, we can design that with a thin film stack. So this was 3 layers of silicon oxide, silicon carbide and silicon oxide, approximately 300 nanometers thick each. And we're able to tune it so you get something that absorbs very strongly at exactly the same wavelengths where the sky window is transparent, but it also reflects at the high angles so you don't see the horizon. So making a thing like that, we can get very cold temperatures by just sitting out a surface out in the sky, outside. So we put this sample outside. This was done in, I think it was about June, so it was like a late afternoon, so that's why the temperatures are cool. So you see that the selective emitter started off warmer than ambient because it came out of our lab, walked outside, had it all plugged in, turned it on straight away. Within the first hour, it had dropped from above ambient down to 0 degrees C, even though ambient temperature was 14 degrees. So we're making ice straight away. So this is set up not in direct sun, so it was shadowed because it's late afternoon in June. You can do it just in diffuse, so you're still getting 50 to 100 watts per square metre of sunlight coming in, but we're still getting significantly subambient. These films, because they're silicon carbide, silicon oxide, are relatively dark, so that's why we sort of had to go, these were aimed for nighttime sort of experiments, but we managed to get quite good cooling even in the late afternoon. So that was in 2010 we were doing that. So that was a piece of glad wrap to stop air warming the sample back up. If you don't have the glad wrap there, you end up getting limited to about 7 or 8 degrees below ambient because you've got a cold surface, the wind blows past it, it just gets warmed up because of the amount of convection you get. So if you look at it over a couple of days, stayed subambient the whole time. what you'll see here is that one surface was a black body, or 0.95 emittance. The other one was a selective emitter. So you can see the selective emitter is able to get colder than the other one because of the temperature regime we're operating in, where there's not much thermal load and we're significantly subambient. And so, yeah, this one stayed very cold. So overnight it stayed at 0 degrees. You're getting up to 10 degrees during the day. But because you could have, you know, if you've got a surface which is cold and you have it above, say, an esky, you can set it up so that the cold air, when the surface is cold in the esky, the cold air flows through into the bottom. So we built a little esky that we put beers in up on the roof of the lab. And so we had this sky-cooled esky and a solar cooker. So you could have it set up there the night before. You could throw some beers in. That morning you could throw some pies or some sausages in. Go up there at lunchtime, you'd have some hot solar cooked food and some ice cold beer from the sky, which was quite a fun one to give on tours when you have people doing that. So, as I was saying before, it sort of depends what temperature you're at. And this is one that we're still trying to get across to some groups that work in radiative cooling, is when you're better off having a selective emitter. So you've actually got to look at the radiative flows at all the different wavelengths and then work out the total power and see that you're actually better off at most real world cases. So if you're doing it on roofs or solar panels, if you're above ambient temperature, you're better off with a black body. There's no question about that at all. But once you start to drop below about 4 or 5 degrees below ambient, a selective emitter may be better, but you have to be able to get into that regime. So if you've got two surfaces that go out at the same time, the selective emitter will cool slower at first than the black body, and then the selective will take over once you get colder down. So it's sort of this trade-off, but most of the time you're not going to get into that regime unless you've got something where you're trying to just get very, very cold temperatures with very low thermal mass. So yeah, if you're doing solar panels, really, really high thermal emittance is what you want to aim for. And if you're aiming for, if you end up with a trade-off of you can't get really high at all wavelengths, you just want to make sure that in the sky window it's really high in there at least. So with glass, for example, there's a peak in the reflectance right in the middle of the sky window, so you really want to get rid of that to make it work better to emit. So yeah, basically here, black body emitter maximises the thermal output you can get. So if you're hotter, because it's basically your sigma T to the 4 gets multiplied by emittance. So the hemispherical emittance really matters once you're warm. So first one I was talking about there was spectrally selective. You can also do spectrally and angularly selective. And then there's another case that you can look at where you've got a black body emitter and then you have a heat mirror on the side. So basically like a silver mirror. So with that, you can emit at all angles, but you only see the sky directly above. So if you end up doing that, you've got the advantage of the black body, but you're also blocking the incoming radiation as well. So I'll come back to that one, but we've, at SPREE last year in San Diego, I presented some stuff where we made some parabolic coolers so you can put it out in the sky using basically those techniques. So that's all about nighttime. Daytime is exactly the same, but you want to get rid of the sunlight as much as possible. If you're above 90% reflecting, you can be below ambient almost the whole year. If you're above 95%, you can be below ambient all the time. So basically, if you've got 5%, you're getting about 50 watts per square metre of sunlight being absorbed, and that's about how much you can radiate out and stay at or below ambient easily. But that's, if you look at where the sun is during the day, even if you've got, say, something 85% solar reflecting, because it depends on how much is being absorbed, when the sun drops to the lower angle, then you can actually be cooler than ambient quite a bit of the day, even if it's not a really, really high reflectance. But in the middle of the summer, you'll still get the peak because you start to get the 1,000 watts coming in. And this also depends on which direction your roof is. So big warehouses are often very flat, and so that you get one effect. But if you've got houses, you'll have a north-facing roof and a south-facing roof. The south-facing roof, if you've got a fairly good reflective paint on it, that can be below ambient significantly more time because of your cos theta angle to the sun. So summertime, most of you probably know about the Stanford guys, FAN. They published this one in 2014, the end of 2014. They made this, it was advertised very broadly and it was quite good. We saw that one and went, yeah, we had this sort of experiment in our mind that we've been planning to do for ages and never really got around to doing it. They published that one and went, okay, we'll do the experiment. So as soon as the paper came out, we turned around and started to do the experiment that we needed to do we've been planning to do for quite a while. So their one, basically it was in the time of the year where you got about 850 watts per square metre onto the surface. And they had convection suppressant over the top to make sure you don't get wind warming the surface back up. So that was the two things on that one. We went for fully open surface, like a roof surface, to see can you get below ambient with wind warming you back up at the same time, and in actual full sunlight. So we had 1,060 watts per square metre, and you can actually still get below ambient. The length of time of how many days you can stay below ambient gets limited by how much dirt you end up picking up. So because we're based off Harris Street, most surfaces get pretty dirty there. So you see the temperature creep back up towards ambient, but any surface where you're aiming for above 96% reflecting doesn't take very much to start to absorb that extra bit of heat. But yeah, so basically this was the thing. We basically set it up on top of one of our cubbies. We had this, so you got this is standard colour-bond roof, and so this is our surface on top of a styrofoam box measuring the temperatures in behind it. So that's sun's not actually behind that. That was just throwing multiple pictures together to make it look pretty for a image we put together at one point. So this super cool material, basically it's 96% solar reflecting, so it doesn't absorb very much sunlight. If you look at the spectral response, so all angles reflects very well. Once the solar there's no longer any solar, it's absorbing very strongly. This is the transmission of the atmosphere. So in the sky window, it absorbs very strongly, and then at longer wavelengths, where the sky is not transparent, it then reflects again. So it actually works out quite well. And so we're able to get sub-ambient temperatures on that one. That one ended up being picked up quite well by lots of people. Since then, recently, I think it was the end of last year, the guys at Stanford then published combining super cool roof with a air conditioner to try and use a radiative panel. So for that paper, they used this material. So they went and put that in. So that was good to see they listened. There was a good way to do it, because they were doing it with these really complex multi-layer structures. This is based on a 3M multi-layer polymer, which is an extruded piece, and then we're doing a silver coating onto the back of it. So the material normally gets used for back reflectors. So it's called their enhanced specular reflector film. So you can use it in back reflectors in phones. People have also used it for concentrating solar, because it reflects really strongly up to 1 micron. So you put that on as your mirrors on there, you can get the sunlight for the silicon cell, but not get the extra heat. So there's a couple of other things people used it for, and we went, that's cool, let's coat at the back of it so we can actually get the solar reflectance in the near infrared up as well. So getting back to black body emitter with edges on it, so you want to then have a mirror. Years ago we tried to make these things and went, this is really hard, you have this big problem of getting the thermal conductivity. So we used, you can get parabolic reflectors for light fittings. So we've tried out a few of those, but you're getting too much conductivity down them. It never worked very well, so we went, put that idea in the bin, until we got a 3D printer and started playing with it. And went, we can design these, so you can use a CAD program, design your perfect parabolic reflector, which reflects down to a surface, and then 3D print it. So printing it in ABS, 10% infill, so it doesn't conduct very well. And then when you 3D print, you get this sort of rough surface. You can reflow with acetone. So put some acetone on it, you can get a nice polished surface on it. After that, then we put it in the vacuum chamber and then sputter it with silver, so you get a really nice reflector. These photos here, where you can see it's reflecting down and focusing down to a point there, that's before the silver coating. So this is just the plastic that's had acetone put on it, and you can already see that it's focusing down quite nicely because of the high angles that are involved there. So this one here was like 200 by 200, 140 mil base on it. And so using that, we can put that outside and then get very cold temperatures once we do it. So when we first made this, it was all sort of done by, this should be the shape and that looks good. Afterwards, we then did the experiments, worked outside, then went, okay, let's do the ray tracing on this and check that we had it right. And so using a good way to do ray tracing on all these sorts of things, instead of using the scientific software, because all animations are done so well with physically correct models these days, you can use software like Blender. And so analysing it over a whole year, because you can track where the sun is, how much sunlight is getting in, how much diffuse light. And so we modelled the whole thing. So this one was set up with a front sunshade, so it's in diffuse only. Because one of the things about a parabolic reflector is that not only does it concentrate how much sunlight or how much sky, how much radiation is going out towards the sky, it also concentrates how much sunlight goes in, so that will increase as well. So if you do it in diffuse light, you can design it so that you get shadowing across the whole time. And so you can see quite reasonable agreement between those as well. We did a whole bunch of different models of looking at what area of the sky it actually sees. So does it actually reflect up and just see the top? And then also put these ones, so a few slides back I had the one where you can measure how much sky radiation is coming down. We printed out parabolic reflectors exactly the right size that could fit over those sensors, put it on, and you see a 10-degree drop in effective sky temperature by doing that because it's blocking out the high angles. And so when you do that to a surface, you've got ambient temperature, you have 10 degrees below ambient, and so this was in October. So the other stuff we did previously was in June. This is October. You've still got diffuse sunlight coming on, but we're sitting 10 degrees below ambient over multiple days continuously. And so that's basically because you're blocking the high angle. So you can see how much diffuse we've got. So we've got basically global horizontal solar and a shadow band, so we can work out how much diffuse is going in. And so even on this day here where you're getting about 200 watts because there was some patchy clouds. So when you have if you had full clouds everywhere, it's not going to work because you'll still be concentrating towards a big cloud which is warm. But if you've got patchy clouds where you get extra sunlight coming in because it's bouncing off the cloud and in, you can still get with 200 to 300 watts, you're still getting 10 degrees, or in that case up to 5 degrees below ambient temperature continuously, which is quite a fun little game to play. So it's just looking at spectrally all different angles of not just your surfaces but the environment around you as well, and exploiting that as much as possible. So we also, we'll say before, we do stuff with some paint companies as well. So SkyCool is a company in Sydney that we've done stuff with for years, and they gave us this video. They were painting one of their roofs and they had a thermal camera up there. And so I think this was like a 20-degree day in the afternoon, so you can see surface on this side, the white painted roof, which is very white, 4 degrees above ambient. That's pretty good. This is a standard old zinc aluminum sort of roof where it's aged, so you've got, it absorbs a fair bit. The emittance is about 0.5, so this actual temperature is really hotter than that because the cameras are set up for 0.95 emittance, which is about the same as what the paints are. So you can see here a couple of interesting effects. One, cool roofs work really, really well. So if you look at the microclimate on a cool roof, or of any roof, when you're modelling, say, an air conditioning system, you look at the temperature of the air that goes into the air conditioner, and people will take the surface temperature of the roof and the ambient temperature, and it's halfway between that will be the temperature of the air that goes in. One of the problems is, if you have a cool roof, that works pretty well. When you have a hot roof which is sitting up 63 degrees, no one ever thinks you've actually got significantly warmer than ambient temperature going into your air conditioner. So all the modelling software currently that exists work really well for cool roofs, but they actually don't work properly for a standard roof because of how much hotter the air temperature is. So how that works for solar panels, if you're putting, so on houses, not going to make much of a difference, but if you've got large-scale warehouses that they're going on to, and you're putting on relatively small areas of panels, the local ambient temperature of the air is going to be different depending on whether it's on a cool roof or not. So if you, like, you guys are the sort of people who should be encouraging as much as possible. You know, if people have done some papers on, use cool roofs, it'll make a bit of a difference, but it will make significant differences. So doing some real-world testing on an old zinc aluminum roof and a cool roof to see the difference in efficiency of, you can get a building where you've got half of it painted, you can actually see what the actual efficiency differences are and then try and push people into doing it properly, as opposed to putting it on an old roof, because often people say, we're covering up the roof anyway, so it doesn't really matter how much heat's going in there. But if it's not covering the whole roof, you're going to get warm air blowing past, which will then change your module efficiency. So you can see up here, these bits aren't painted. So these don't actually look that dark, and they're still ridiculously hot. They also made a nice video of when they're painting the roof, so you can see how quickly the temperature actually drops on these things. So they've got this nice paint thing where it's this sort of width. They just walk along, spraying it as they go. And so you can see after very quickly, so this is a metal roof, so it has some thermal mass, so it takes a while to actually cool back down. But you can already see it's starting to drop down quite quickly down to the same temperature of the pre-painted roof. So if you've got a building and it's painted straight away, almost straight away you'll get the effect inside. So one of the things people look at with heat modelling of buildings, for example, you go, how much energy is being used for the air conditioner? One of the other things they don't often think about is when you've got a dark roof, the air conditioner is often cut out, and that's a big problem for businesses. If you have a building which is thermally efficient, the air conditioner no longer cuts out. It'll only be running at a lot lower energy usage, so that way you don't actually wear out the air conditioner as often as well. So this is a shopping centre out in Western Sydney, and after the roofs got painted out there, they found they no longer had this problem of the air conditioner cutting out on the really hot days and then having to close the shopping centre. So that was the sorts of things, which then carries across to lots of different areas. So that's, I sort of said, how does that relate to it? Basically, cell temperature affects performance of your cells. If you look at putting them on and encouraging people to put it on white roofs as much as possible, that's what you want to do. And all the techniques we're using for doing all this different spectral control, you can do the same thing on modules. So up until quite recently, most people doing silicon cells go, yep, we measure up to 1300 nanometers. Past that, who cares? It's just, that doesn't get used at all. So measuring across full wavelength spectrum from UV out to 25 or 50 microns, measure the whole thing, do proper thermal modelling, and see where can you actually fix things up. So if you've got, if you have different coloured the encapsulants around them, if you want to make sure, I'm not sure if people have looked at, if you're looking at how densely packed your wafers are over a whole module, how much effect that's going to make on changing the whole temperature. It's the sort of things you could look into as well, which would be quite interesting. And yeah, so the microclimate around the roof. So that was sort of that sort of side. I'm also going to talk about some of the transparent electrodes we've done and a few other different bits and pieces as well. So this is stuff we're doing with in the cluster work. So in this one, we were basically making the electrodes. The guys at Queensland were making devices. They'll do some testing on, send it back to us, and then we'd measure them, do optical analysis on it, then say, let's iterate, make some new ones, and change it. So basically, these are the 1-inch square slides, so you've got this small little dot on them. And so if you want to look at how much light actually gets absorbed by the cell, we're doing ellipsometry on the little pad. And so because you can take the film, instead of doing, if you ever do ellipsometry and want to know exactly what's going on, you don't want a single sample, you want to have the sample in a couple of different scenarios. So in this case here, you can have it where you've got an aluminium back reflector in there, or you then model it and measure it in the other part where you don't have the back contact. Then you have two different measurements of the same interesting part of the material, link the model in WVAs, and then try and get the exact thicknesses out of a multi-layer stack. And so in this case we had, so you had this, well, so it was glass, aluminium zinc oxide, silver aluminium zinc oxide, a moly oxide buffer layer, so you get the right work function, then the P3HT, and then your aluminium contact on the other side. So you're able to measure it in different spots. So in one spot you'll have aluminium, in the other spot you'll have glass behind it. And so having those two combined, you can get the optical model working well, and then prove that you shouldn't ever use a deck tack to measure the thickness of a polymer, because the deck tack will just drag straight through the polymer and give you the wrong thicknesses. And so in this case we ended up throwing it in one of the SEMs and doing cross-section on a device so we could show that what we're getting from the ellipsometry matched the actual device, and then say, look, stop using a deck tack to try and measure the thickness of a polymer, it's a waste of time. And so we did PV and some OLEDs. So this one on the bright one on this side was using our stack design, and one on the other side was using a standard ITO contact. And so with this one, doing this AZO, silver AZO, you can see it's slightly more transparent than an ITO glass slide at the relevant wavelength for the design we're doing. So this one here was designed for transparency in air, which is usually when people do metrics of electrodes, transparent electrodes, they say, what's the transparency in air and what's the sheet resistance? So the ITO sheet resistance was 15 ohms per square. Our stuff was 8.4 ohms per square, so significantly lower. You could bend it, even bending it quite tight, you'd still stay above or below 10 ohms per square because you've got a very, very thin ductile material between the oxides. So rather than doing this silly metric of saying in air how transparent is it, you want to optimize for what's the actual, when it's put into a device, how many carriers can you actually generate, and then generate it in the right spot. So you do your electric field modeling and actually work out where it goes. In this case, we ended up having it where we generate significantly more carriers because it's a resonant cavity between the silver layer and the aluminium layer. But because of the distribution of the electric profile, it was slightly closer to the anode. So you ended up getting some recombination on that side because the moly oxide actually leaks a little bit electrically. And so the other interesting thing here, so you can see it's absorbing more light. So it's absorbing out to here. This big dip there is actually with moly oxide, it's not MOO3, it's a suboxide to actually get it to be the right work function. And so that's the big absorption band you see optically from it as well. So when you're doing an oxide contact, you need to know what the work function is so you can go, will it work in my device? So this will apply for any of your other materials, your devices you're making. So AZO is actually quite similar to ITO. It's about 4.6, 4.7 EV for the work function. Moly oxide, ideally, to contact P3HD, you're wanting it to be 5.4 EV. Fortunately, if you take moly oxide, evaporate it in a vacuum chamber at the appropriate sort of rate, it gives you exactly the right work function. If you sputter it, if you start with a metal target or an oxide target, you've got to either reduce or oxidize as you go. So this is some stuff we're looking at, changing the so starting with a metal target, changing the oxygen flow rate to get different from MOO3 down to where we need. So we had to have an instrument to be able to measure this. The guys at CSIRO had a PESA instrument where you could send the samples off to them and then get a response back in a couple of weeks and get the sample back, which was excellent and worked really well, except you couldn't iterate and make an next sample and test it all out. Particularly because we weren't making the devices ourselves, so we couldn't go iterate, throw it in a device, does it work? No, make the next one. So we went, build up this instrument. Basically, you've got a UV light source that comes in, a vacuum chamber, which is at a sort of not particularly good vacuum. So it's basically a roughing pump with a little needle valve here that's set open. Measuring the pressure. This is all set up really small because it was designed for doing our single slides, so little 1-inch square slides. You've got a 500 volt probe above the stage, and then the stage is earthed through an electrometer, so it's a picoammeter to measure how much current is going through, and it's gas cascade amplified, so basically works the same as your ECM detector in your electron microscopes. And so you end up getting electron comes out, ionizes the gas, and then it continues to cascade, so you can measure a current that comes through. So you can take that data and then compare it to the PESA instruments, which is the commercial instrument you can get. And we also did comparisons with UPS, and often you'd find that the measurements from this or PESA would be more relevant for when making a device than if you used UPS, just because once it goes into UPS, you end up put it under a vacuum, and moly oxides, for example, the oxidation state changes, and then your work function shifts, and you no longer have it working properly. So in this case with moly oxide, we went all the way from MOO3 through to MOO2. And so because basically you end up having a defect state which comes in about 1.5 EV above the valence band, which is then gives you the right work function. People usually just call it work function for a contact. It's not work function. It's ionization potential or a ionization defect state, which is doing it. But generically people just call it work function often. So this is a slide from the guys who make the PESA instrument. Saw it online, described it nicely. So for metal, it's a work function. For a semiconductor with no defects in it, you're measuring the valence band. If you've got something else, it's really the highest occupied state. So if you've got defects in it, and you've got the valence band, some defects up here, that's what you're seeing. And that's usually what works as the thing that's contacting your devices, So some other random things we've done. This came about from Salius from Swinburne. He gave a talk at UTS on some of his black silicon materials he'd made ages ago, and they were doing some pulse measurements on it. And I just asked them if they measured it optically to see what it was like. And they said no, they sent us a sample. So these were, you can see, quite dark ones out to a micron. And so got sent some samples and then went, this measurement won't take too long. It took a very long time to measure it and then try and fit it. So the hard thing with ellipsometry is fitting the data. If you've got black silicon, you've got these nice tapered things, which are some length. Hopefully the people have done TEM for you and they give you the shape and size. Usually that's not going to be the case and it's not going to be right anyway, so you end up trying to fit it. Eventually came up with the model which matched. We ended up redoing SEM on the exact sample we had and then saw that it was this shape. So this is basically the refractive index throughout the sample. So if you start at the top and you've got voids, so that's down here, you got voids and then it goes to a basically continuous silicon at the bottom. And so this was combining a tapered effective medium of mixing silicon and air and a very thin oxide as well, and combining ellipsometry and multi-angle reflectance. And so that was a fun one. So they ended up being a part of their paper where they then did some, they were doing light-induced reflectivity transients. So they were pulsing it with a very strong laser and then doing pulse probe. And so I did those measurements on it. Matt, who's at our group as well, did some looking at, can you model the changes in the reflectance due to temperature effects. So that's basically what ended up looked like, is that the effect they were seeing was due to changes in the temperature of the silicon from the pulse from the probe. It's another one. You'll probably recognize these names down the bottom. So we do temperature dependent ellipsometry as well. Cool. So this was basically looking through and scanning through on a perovskite, going from room temperature down to liquid nitrogen temperature. First of all, did some scans through across the whole range and then narrowed down. So this is over quite a narrow temperature range and measuring it as it goes through the transition. Other equipment we have down there. So you basically have sort of gone over the different ellipsometry, quite a long wavelength range, 190 to 3.3 micron. These guys have come out and used it for that sort of purpose. Temperature, quite a few people have come out and used it for that. Sample mapping, Ivan's come out for one of the ones where it was the silicon, porous silicon one, and looking at how thick the layers were. So we went out to quite long wavelengths, then mapped across it to see what was going on. Ning did some stuff with one of our spectrometers where you've got, so instead of just taking the hemispherical reflectance at normal incidence, taking a hemispherical reflectance at variable angles as well inside the centre mount sphere. So David, who's now at Macquarie Uni, isn't he? He's I've got some samples from him at the moment which are from here, on doing some BIDF measurements to compare it to what you guys can get. We've also got an FTIR set up for variable angle reflectance transmittance and building it into the ellipsometer as well. So we've got dual polarizers on it. The ellipsometer one works all right. It's mainly being used for reflection transmission though these days. And we've put temperature stages on this as well, basically because we also work on things like vanadium dioxide, which have metal oxide transition from an insulator to a metal at around 68 degrees C. So we've got quite a few stages which is designed from room temperature to 100 degree. So then we can measure that from UV out to 25 micron and get refractive index data across the whole thing. Rotating cavity emisometer, so if you just want to look at the emittance of a surface. The PIS, which I was talking about before, in situ monitoring of annealing. So we've got some chambers where you can heat it up to 1000 degrees C and monitor the reflectance or the emission off the surface while you anneal it. So if you want to see what temperature does something break down, how does it break down, or if you put a mixture of metals together, what temperature do they alloy at, those sorts of things. And yeah, always happy to do that. A lot of you might know about ellipsometry. Basically, have a polarized light source on one side, bounces off the sample, then you look at the shape of the polarization on the other side by a polarizer rotates around. Fairly easy measurement if you're doing straight samples. Adding temperature dependence, those sorts of things becomes more complicated. And also it's just the fitting the data is the hard part. So yeah, we've got the sample mapping. So this was a spin-coated one. You can see it's thicker on the edges. So if you take a spin-coated or a sputtered sample, you can see the comparison of how thick they are. So we've got temperature stages. If anyone ever wants to get liquid helium, we can go down to that. Normally we do liquid nitrogen up to 800 Kelvin. And we've got this one we've made recently where we can do air. So it's done with a Peltier, so you can go from 0 degrees to 90 degrees. in air, so we can do quick sample changes on them. Then we've got the Bubba Fett. So this one came about because the technician who installed it told us that at their Christmas party one of them put the cover on their head and ran around. So that's why it's that one. So the UMA, basically you can measure BRDF measurements. So you can vary the angle of incidence and the angle of the detector separately and across all different wavelengths. And we've got polarizers on that as well, so you can do polarization sensitive things. So standard reflectance sort of things, plus hemispherical reflectance, R&T, or variable angle hemispherical. So center mount the sample, rotate it around. So this was throwing a diffraction grating on there, scanning across different wavelengths, different angle combinations, so you can see you get quite nice data out. This is scattering, taking a matte paint and a semi-gloss paint, and so you can see the matte paints are actually quite good up until the very highest angle there, where it's actually missing the very end of the sample because you've only got so long you can go. This one here, you can see the specular reflectance is down the center there, and then how much scattering you get. So you can see here that, as you notice, if you see any surface that's glossy, it reflects quite high at high angles just because of the binder material that's in there on the outside. So that same thing occurs in the infrared. So if you've got a very smooth surface, it reflects highly at the high angles, so you don't emit very well. So one of the things we'll look at is the effects of surface texturing on emittance. So if you take that data there and then look at just the specular component, you can see that a semi-gloss thing, so this is not a fully shiny, this is just a, like a Colorbond roof sort of level semi-gloss, goes up to quite high reflecting relatively quickly, and a matte surface actually does eventually start to go up as well, but it can be a lot lower. And so yeah, they're the sorts of different random measurements we do. And thanks for listening.
Thank you, Angus. It was great. It seems that we have class after us, so maybe we can take some questions outside. And if you go out, just take some stuff to help us. So thank you again, Angus. It was great.
Thanks.